to go to the next slide. All right, just one announcement I know of that not all that important, but just in case. I know that just all of you work full time, so you probably wouldn't be looking for me. But if you were going to try to get in touch with me Friday, normally on Fridays I'm on the Birmingham West Campus from 8 to 12. This Friday I'm not going to be there. I've got an infusion this Friday, and I'll probably be starting by 8 or around 8. So no way I'll get there before, and it usually goes way into the afternoon, so there won't be any way I'll get there afterwards either, mostly because I shouldn't even be driving afterwards. They give me Benadryl, and that sort of knocks me out, so to speak, makes me really tired, so I probably shouldn't drive. So I go home and go to bed. Okay. Ashley, right? Yeah, okay. Slowly, I'm learning most of the names and faces. All right. 2, 3, 4. All right. Okay. Any questions on anything we've done so far? Yes.
On the homework, section 16.2.
16.2, got it.
On number 15.
Number 16? 15, okay. Okay. So this is page 435. Whoops, let me get my pen set up. Page 435, I said, or 25, I can't read. 35. This is problem set 16.2, number 15, you said?
Yes.
Okay. Find the wavelength, so we're looking for lambda, okay, of a wave traveling twice the speed of sound, okay. I'm going to put it velocity is equal to twice speed of sound, okay, that's what that stands for. Speed of sound is 331 meters per second. So let's just go on and call that 2 times 331. 331 meters per second is equal to 661 meters per second. Why in the world they phrased it that way, I don't know, okay? And this is Jennifer Addison, right? Okay. All right. Now, we're doing problem 15 on page 435, 16.2. Okay. That is produced by an oscillator emitting 63 pulses every 8.3 times 10 to the negative 6 minutes. Oh, what a nice round number. Okay, so it's 63 pulses in 8.3 times 10 to the minus 6 minutes. Okay. All right, a couple things to do with this problem. Okay, this is related, that last bit of information is related to what concept?
Frequency period. Like it's related to frequency equals 1 over a period.
Right.
So it means, if I'm correct,
Yeah.
63 pulses in.
Right.
So you take, but this is in minutes, which is a
Right.
problem because we need it in seconds.
That is our first step, is to take it to seconds. So how do we get minutes to seconds?
We put minutes on, like we say 60 seconds.
Right.
1 minute.
Okay, you put seconds in the numerator, minutes in the denominator, and that would be 60 seconds is 1 minute, and then you multiply and see how many seconds that is.
And see, I did that. I don't know if I was
Well, let's see. It's going to be 498 times 4.98 times 10 to the minus fifth, maybe, or minus fourth.
Yes, 498.
4.98.
Times 10 to the, I have 10 to the 8.
Whoa! Okay, try that again. Did you put negative 6 or a 6? Okay. 8.3 EE or EXP minus 6 times 60, 60. That'll give you 4.98 times 10 to the minus 4, I believe it is. What do you get? What do you get?
I'm still, I must,
No,
I guess I'm not getting that.
no, tell me what you...
Well, it was still the 4.8 term. I'm not getting to the negative 4. That's not me doing
Well, I might be wrong. I'm doing it in my head. So, did you get 4.98
I did get 4.98.
times 10 to the what?
Let me try one more time.
Okay.
I'm still getting 4.98 times 10 to the 8. So I must,
Wait.
maybe my negative's not working.
Okay. Okay. Different. Are you using a phone or calculator?
Well, I'm using my phone because my big calculator is so incredibly confusing.
Okay. Yeah. Okay. You put negative 8?
I did this for the negative. Like I did 4.98.
Okay. Right. Okay.
I
All right.
mean, 8.3.
Okay. Ooh. Get back.
Well, I've got this.
Here it is. Okay. 8.3. Okay.
And E is right there.
Oh, it is. Okay. And then what you do is 6, and then you do a plus minus. That's how you do a negative on this screen. Yeah. Times. Yeah, there it is. That's the correct thing. 60. 6, 0. 4.98 comes into the minus 4. Okay, or you can leave it like that if you wanted to. All right. So that then gives you pulses per second. So what we do, we're looking for wavelength, and how is that related to velocity and frequency?
Well, the pulses per second. That's frequency, right? I mean,
What's that?
isn't
Yeah,
that
that's frequency. Yeah.
So when we use the formula, velocity equals wavelength times frequency.
Okay. Velocity equal wavelength times frequency. And we're looking for wavelength, so that would be divide both sides by frequency, right? Okay. So that would be wavelength is equal velocity, 661 meters per second, divided by, no, that's time, okay? It's 63 divided by that, pulses per second. So it's 63 pulses, okay, divided by 4.98 times 10 to the minus 4. I didn't write it down. Minus 4 seconds. Okay. Pulse isn't really a unit. This is just per seconds. Now, to do that easier on the calculation is this. 661 meters per second times, when you divide, you invert and multiply, and that would be 4.98 times 10 to the 4 minus 4 seconds divided by 63 pulses. Okay, that's not a unit down there, it's just what that represents. Okay, so you take that and you see here the seconds cancel out and you get the meters per pulse, which is your wavelength, or at least that's what I hope it is. Okay. So that's going to be on the order of 5 times 10 to the minus 3, I think. Somewhere in that ballpark. No, yeah.
Yes.
What?
Yes, I got 0.005. So it is 5 times 10.
Okay. Yeah, but give me 3 digits. Or maybe only 2. 2 or 3. 2, I guess. 5 point what? 2 times 10 to the minus 3 meters, which would be 5.2 millimeters. 10 to the minus 3 is milli. So is that close to the answer they have in the back?
Yes, that is.
Okay, good.
Okay, so it's meters because a wavelength is measured in meters.
What's that? Well, it's a length measure. Wavelength is a length measure. So meters would be good. And since it's 10 to the minus 3, it's just easier to say millimeters. But 10 to the minus 3 is fine, meters. Okay. That is the SI unit, but just takes less.
And then I know I shouldn't have a question about this one. I know it's supposed to be easy, but I don't understand the way they wrote the answer in the back.
For what?
Number 1.
Number 1. All right, to erase this one, everybody? Okay. All right. Okay, same page.
Yes.
Number 1. Find the period of a wave whose frequency is 500 hertz. We're looking for period. What symbol for period?
T.
Capital T. That's what you don't know when the frequency F is 500 hertz. But what is a hertz? That's a per second, 1 over second. Okay? Pulses per second, cycles per second, something per second. Okay? That's what we were dealing with before. So, period is equal to 1 over frequency, which should be the reciprocal of that. And I should have put the bar over that, but okay. And if you do just a few decimal places here, that would be 0. Let me do it this way. Move it 2 decimal places there. 0.00, maybe one more 0, 2 seconds. So that would be 20 or 200 nanoseconds, no, microseconds, or 0.2 milliseconds. I don't know.
They had, and I didn't know what it stood for. I think they had, yeah, 2.00 ms, and I didn't.
What's that?
2.00 ms. So is that milliseconds? They just have ms.
Huh? 2.00. Maybe I did my calculation wrong. Oh, I did. I moved the decimal too many places. Yeah, it's 2. I'm sorry. I was misreading my mark there. I went 2 places. I thought I went 3. So that would be 0, 0. I'm sorry. I botched that one up. 0.002 seconds, which is... And because we have 3 significant digits, that would be 2.00 milliseconds. That would be 2,000 microseconds. That wouldn't make any sense to even do that, so we'll take that one out of there. So either 0.002 seconds or 2. And actually, if you wrote it this way, you should write the extra 2 zeros because we have 3 significant digits. And so it's either 0.00200 seconds or 2.00 milliseconds. The reason is you had 3 significant digits here, you need them down there. Because milli means 10 to the minus 3. So that moves the decimal 3 places that way. But you need the 2 zeros because you had 3 significant digits there. I was doing it in my head because I don't have a calculator over here, but my reading my writing was what threw me off. Okay, and look, if you have 0.00200 seconds, perfectly correct, you know, lots of ways to write the answers.
So again, that formula for frequency is saying the reciprocal of the period. That's what that
Right, yeah.
is.
You can also do frequency is equal 1 over period. That's also true. And period is 1 over frequency. They just go back and forth. Okay. Good questions. Any others? Yes. Okay. Okay. Ooh. Okay. Let me, before I mess up somewhere, let me mark my place. Okay. Okay. Back in chapter 12. Okay. About what page? At the end of the chapter. Okay. Okay. Review questions or review problems? 340. I got it. Yeah. Oh, I'm sorry. I'm sorry? Chapter 12 test? Yes. I'm sorry. I don't hear well. Okay. Okay. Someone pull yours out and tell me how does it begin?
A force of 32.5 newtons.
Say that's how it starts.
It does. Number 1 begins with a force of 32.5.
Yeah, got it. Well, thought I had it. Okay, find the acceleration was the first test. Find the work was the second test. Here it is. Find the work, find the work, find the work, find the acceleration, find the work, find the work. Hey, there it is, a force of. Okay, let me show you something. Here, they wrote something that made no sense. This should be 50,000 pounds. They put 50, comma, and only put 2 zeros. Should be 3, so that's what that means. Same thing here, that's 60,000 pounds. I think those are the only corrections on that. All right, anyone else need that test? Okay.
The first one is number 6.
Number 6. Okay, so that's page 340. Let me go on and go to a clean sheet. Is that okay? Everybody got it? Okay. Page 340. Chapter 12, review problems. Number 6, you said?
Yes.
Okay, number 6. A cylindrical piece of aluminum is 4.25 centimeters tall. Basically, it looks like a tin can. Okay, that should look better than that, but that's what. So the height here is 4.25 centimeters. Okay, and this is aluminum. Okay, cylindrical piece of aluminum is 4.25 meters tall and 1.95 centimeters in radius. Mine is probably not to scale. Okay, so the radius here is 1.95 centimeters. Definitely mine's not to scale. Okay, how much does it weigh? So we're looking for the weight. okay, of this object. What will your answer be in? What units? Okay. That's your unknown. What is it? I thought I heard someone say it correctly. Okay. That's in the U.S. customary. These measurements are in not SI, but metric. So what do we usually do the weight in metric? Now, in the back of the book, does it give it in?
Kilograms per meters.
Okay, kilograms is a mass unit, not a weight unit. Newton, okay. So we want it in Newton. And what is a Newton? Remind me of what a Newton is. Kilogram meter per second squared. Mass times acceleration. Okay? So, a couple of things we have to do. We have to get these measurements into meters and then go from there. Okay. Well, before I do that, we also are going to be using what formula?
The one that's got the radius in it.
What's that?
The
It
one
relates, huh? If you look up in a table, what are you going to find about aluminum? Only table we have in this chapter. Back on page 330.
Weight, density,
And mass density.
mass density is 2,700
Kilograms per cubic meter. Okay, so since we're going to be in those units, then let's go on and get these into meters. Now they're going to be incredibly small numbers, okay, but let's get them. So 4.25 centimeters. You might know how to make a conversion right now, do you? Without having to do these.
You just move the decimal
How many places which way?
2 places to the right. No. 2 places to the left.
Absolutely. So yeah, that's the easy way to do it. 2 places to the left. Oops, I did 3 again. I'd like to put a leading 0, but then I put the decimal in the wrong place. Okay. Okay, 2 places to the left. Okay, so the height is 0.0425 meters. And what's the radius? 0.1. 2 places to the left. 195 meters. Okay. Now, that's the first step. Next step, we need to get the volume. Because like you said, we need mass density, which is mass per unit volume. So we need to know a volume. That's why we have these measurements. What is the volume of a cylindrical object with a radius and a height? No, that's a sphere.
Oh, length times width times height. No.
Okay, but that's a cube or a rectangular parallelepiped, actually.
It's something squared.
Yeah.
It's radius squared.
Okay, radius squared, that's in there. Okay, let me give you a hint. It's the area of the base times the height, right?
Okay.
And what's the area of the base? That's a circle. What do we like to eat? Pi r squared, okay. But I thought they were round. Okay, pi r squared h. That's the volume of a circular cylinder. I think that's what they specified, didn't they? They said a cylindrical piece of aluminum. So that's, they're assuming you mean, I'm assuming they mean a circular cylinder, okay? So that would be pi times 0.0195 squared times 0.0425. And that will give you a volume in cubic meters. A terribly tiny number. Anyone got it?
Got 1.616065.
Okay, say that again. 1.616. We can stop there. 1.616, is that right? Times 10 to the, or does it have any times 10?
Well, my calculator is showing the E.
E, okay. That means times 10 to the -5 meter cubed. Okay, that's the volume. Okay, and the table that we looked at told us that the mass density was 2,700 kilograms. So the density, mass density, is equal to 2,700 kilogram per meter cubed. Okay, and since that gives us meter cubed, we can multiply the density times the volume. That would give us kilograms, right? That gives us the mass, but they asked for the weight, so what do we do to that? See, this is a multi-step problem. Okay. Now what we're doing here is using the formula rho equal m over v, and solving that for m, so multiply both sides by v. Okay, v's go out here. Mass equal density times volume, and that's why we multiply to 2,700 times 1.616 times 10 to the -5th meter cubed. Meter cubes go out, and you get a much smaller number, but still fairly small number. And this is going to be mass now, not density. This calculation goes down here. So what is that? 2,700 times. You don't even have to erase your screen. If you have that big old long number, 1.616, blah, 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 times 10 to the -5, multiply it by 2,700. If you don't, multiply those. That will give you so many kilograms.
Well, when I multiply by 2,700, I
Yeah.
got
0.0436? Is that right? Is that what you said?
Yes, that's right.
Okay, and that would be kilograms. Okay, now that seems reasonable because this is 10 to the -5, this is 10 to the 3rd, so 10 to the -2 sounds about right. Okay, then multiply that by what to get newtons? It's kilogram times some acceleration. What acceleration might that be? Huh? Huh? Ooh. Just because it was a
Gravity.
Yes, acceleration due to gravity, which is 9.8. 9.80, I think the book uses, meters per second squared. See, that's the meters per second squared. Okay, so multiply that by 9.8, and you get something pretty close to 4.25 or something like that.
Right. 0.427.
0.427. Okay,
0.428.
0.428,
Eight.
and that would be newtons. So that should be the weight. Is that what they have?
No, I have 1.3.
1.3?
Yeah.
Oh, where did they get off the boat? Okay. Only place I can see that we could have made a mistake was, did y'all multiply by pi too? When you were doing your volume?
I did, but I got a different answer.
What's that?
I did. I got a different answer than.
You got the same answer?
No, a different one.
Oh, a different one. Now that may be the problem.
I assumed I was wrong.
Okay. Pi times 0.195 squared times 0.0425. I wasn't keeping up with that. 3 times 2 is 6. Yeah, that should be a bigger number. What you get?
I have 5.07.
5.07?
Correct. Times 10 to the negative.
10 to the what? Negative what?
Negative 5.
Negative 5. Okay. All right, that might do it for us. So instead of the volume that we did have, put that one in there, 5.07 times 10 to the minus 5, and then put that down here, and that'll probably wipe out this number. Something around 0. I was going to say 1.4, but 1.4. No, 0.14 something or something like that. I don't know. See what you get.
No, I think she's correct because I just realized I didn't add the pi.
Yes, or multiply the pi. Yeah. Yeah. Yeah.
Okay.
So what does that give us? 2,700 times 5.07 times 10 to the minus 5. Just my rough guess is maybe about 0.14 or something like that.
I got 1.37.
Huh?
I
Second.
got 1.34.
Say it one more time.
I got 1.34.
1.34 times 10 to the,
Oh no, I'm saying I got 1.34 newtons.
I'm sorry, newtons, 1.34 newtons. Okay. Is that what you had in the back?
Did you round? Did you like just stop and then multiply by 2,700?
I took, I said the 5.07 times 10 to the negative fifth times 2,700. I got that, and then I said times 9.8.
Okay.
And that's how I got that. What is the back of the list?
It's 1.3.
Oh, okay. Yeah.
1.3. Is that what you said? That's what she got then, 1.3 newtons. Why did they drop decimal place? If they used 9.8 rather than 9.80, that would do it. I guess that's what they did. So I can't answer why, but that's the same answer, 1.3 newtons, yeah. Now, if you converted that to pounds, that would be fine too, but that's another conversion to make.
So
Yeah.
it's okay if
Yeah, you can put it in any weight unit you want to, but this is the most direct because they gave you everything in metric. So it was fewer conversions to do it this way. All right. Make sense? That was a multi-step problem, changing units first, then finding volume, then finding mass using the density formula, and then finding weight using the weight formula.
I don't think I would have gotten this.
Oh, sure you would have.
I was working so hard to get
Yeah.
the answer.
That was definitely a multi-step dance. Okay. One more. Okay. And what's that? Can I go on and erase this one? Anyone still writing? Okay. Which one?
It was number 11.
On that same page?
Yes.
Okay. So I'll just put 11. Okay. Find the mass. So we're looking for mass. Unknown here. Find the mass of 1510 cubic meters of oxygen. Okay, what in the world does a cubic meter measure? What kind of, what?
Oh, what would the measurement be?
Yeah. That is your what? Huh? Someone's saying something. I can't make it out. I heard someone say something. What was it? Yeah. What does cubic meter measure? What? I'm sorry. What? Okay. This, we're looking for a mass. What does cubic meter measure?
That measures the volume.
Yes, that's your volume. This is your volume. Okay? There's your volume. Okay? Let me read on. Find the mass of 1,510 cubic meters of oxygen at 0 degrees and 1 atmosphere. Okay. Now, we haven't dealt with those before, unless, of course, you turn back to the table. What table might we turn to?
It's page 330.
330, exactly.
Density in the oxygen, the mass density of oxygen is 1.43
Right.
kilograms per meter cubed.
Okay, and notice up there by gases, what does it say? At 0 degrees, yeah. So that's why that's on there, because that's what you take it out of the table. So we know the density of oxygen at that same thing. And what did you say that was? 1.43? Kilogram per cubic meter. Okay. So we know the density. We have the volume. I think we could determine the mass, couldn't we? By the way, 1510 is a huge mass. So expect a huge volume. So expect a fairly decent mass here. If we know density and volume, how do we get mass?
We say
Units are your friends.
well, I always have to start from the basic formula.
Right,
So
that's fine.
the density of
Density equal,
mass over volume.
okay? And we're looking for mass, so what would we do?
So we would it's volume times.
Absolutely. Multiply both sides by volume, and that gives you mass. So mass equal density, 1.43 kilogram per cubic meter, times volume, 1510 cubic meters. See how friendly your units are? And that gives you kilograms, which will be mass. You just have to punch in the numbers and see. That's going to be about 2,000, maybe more, 20-something. It's not as high as 30.
2,160.
2,160 kilograms. Got it. That's the mass. Is that what they give you? That's a lot of oxygen, folks. That's 2 metric tons of oxygen. But of course, 1510 cubic meters is a huge volume. That would be bigger than 10 by 10 by 10. It would be 15 times 10 by 10. So 10 meters. This room is about 3 meters tall. So that would be a 3-story building times that same length this way. Yo, it's huge. So yeah, that would be a lot of oxygen. 2 metric tons of oxygen. Is that what they had in the back? Good. 2160. Good.
See, I can't, when I get answers, I can't ever picture what my answers are, so I have no clue if
Right.
it makes sense.
If it makes
I'll
sense.
come up with
Yeah.
that answer.
That's all right. Trust your units and your numbers and your calculators, best you can do. Any others? Good questions, by the way. Do you see why that's true?
Yeah, I can see it. I'm just a little off on the rounding. Like my calculator at 2159.3.
Woo, okay, well then.
I mean, I just want to make sure my rounding because.
Yeah, okay. Well, let's look. That's at most 3 significant digits. That's 3 significant digits, so we round to 3. Yeah. 59 something, the 9 raised the 5 to a 6. Made it 0. Yeah. Good deal. And if you have a number close, I'll just do the rounding for you. I don't take up points for that.
So many rules and stuff.
Yeah.
Pay attention.
Yeah. The nature of physics. Precision. All right. If no other questions, anybody? Then let's move to sound waves. This is on page 436, starting 16.3. So I'm going to erase what we got here. And we've got a little bit of, even though some of those problems use the speed of sound, that was before we talked about it, but we talked about various speeds. You could use speed of anything. Okay. Our ears are pretty remarkable objects. Not necessarily the outside. That's just cartilage, okay? But the workings of them are just really incredible, okay? Even for ears that don't work as well, like mine don't. They're still pretty amazing. The frequency range over which the human ear responds is approximately 20 hertz. Now that's very quiet. Very, very low frequency. To 20,000 hertz. That's a magnitude of 1,000 difference there in the range. Okay, so 20 to 20,000. Now, ultrasonic waves have frequencies higher than 20,000 hertz. So ultrasounds, now, will y'all be working with ultrasounds? Yeah, okay. Those are usually higher frequency. You won't hear them, but they still are a frequency. Okay? Now, sounds refers to those waves transmitted through a medium with frequencies capable of being detected by the human ear and produced by a vibrating source. Ringing bell, vibrating, what do you call the things in your larynx? The muscles that you force air through, and that's what makes you speak. It's really incredible how our voices can do that. Our bodies can do that. And then especially someone who sings well can hit those pitches perfectly, you know. It's amazing. It's really amazing. Obviously, he can't sing well.
Well, and if it gets damaged, I had to have a complete thyroidectomy about 5 years ago, and my vocal cords were damaged.
Right.
And so, like, for 3 months, I couldn't speak above a whisper.
Wow.
You know, I mean, it truly was just...
Right. Well, you speak quite well now, though.
But, I mean, it was crazy, you know, just to think.
Yeah.
Just
Yeah.
surgery.
Yeah, Julie Andrews, y'all know who she is? She had pretty major surgery. I don't think it was a major thing, but something went very wrong in the surgery. And she had one of the most beautiful voices around. She can't sing a lick anymore, okay? Really sad. But mostly her career was behind her, but that was really tragic. But anyway, I mean, she was Sound of Music, Mary Poppins, you know, lots of things like that. So the human ear then picks up those sounds. Wide range of frequencies and wide range of loudnesses too. And the human ear can pick that up. And it's all done through little tiny hairs that are in there that vibrate. And the nerves that pick up those vibrations and somehow communicate those to our brain and tell us what we're hearing. It's amazing. It's remarkable. And how even over a telephone, you can usually recognize someone's voice, you know, just by subtle changes in pitch, tones, whatever, accents, whatever. Okay. sound waves transmitted through the earth may be detected by an instrument called a seismograph. That's what they measure earthquake vibrations through. Seismologists, are people who study that. And they have these stations all over the world too to record those, so you need multiple stations, so you triangulate and find out exactly. Now, why did that happen? There we go. Exactly why or where the earthquakes were. You got to have 3 stations reporting so you can triangulate and find out exactly where the earthquake occurred. Okay? There's just amazing things like this. But because they are all over the world to detect earthquakes, guess what? They also detect atomic explosions. So when a country is testing atomic weapons and they're not supposed to, people will pick up the signal and say, hey, was that an earthquake? Nah, hasn't that got the character? That must have been a nuclear. You weren't supposed to be testing nuclear weapons. So they can detect those. Okay. Now, they go into a lot more detail here, I think, than what you need to have. But anyway, the vibration of your vocal cords, that's the word I was trying to think of, vocal cords, okay, that create your sound, your voice, okay. Sound waves are pressure waves. And we talked about this before. If you hold your hand in front of your mouth when you're speaking, you feel those little pulses of air. Well, those little bitty pulses of air spread out. You can't say something, I can't feel those pulses here, but your ears can detect them, Amazing, okay? They talk about a lot about seismographs. There are 2 types of things. They're not really sound waves. There's seismic waves, but there's both pressure waves, which are longitudinal waves, and transverse waves that we talked about before. There's both of those come across from earthquakes. The pressure waves, they're not sound waves. The pressure waves, the P waves, are a little bit faster than the transverse waves, so that gives them an idea how far they are from an earthquake when they get the 2 different signals in. So each of the stations know how far they are. They draw circles around, and where the circles intersect, that's where the earthquake was. So it's really an amazing situation. Now, musical instruments use those vibrating strings or vibrating columns of air, depending on what kind, or vibrating a drum, vibrating head of the drum, All those things are used to create the different sounds. Okay. Now, any of you know the old rule of thumb. If you see lightning and start counting, you can estimate the number of miles away that lightning was from the difference in seeing the lightning and hearing the thunder. Because every time it lightens, it will thunder. Sometimes the lightning strikes are so far away, you won't be able to detect the thunder. But when you can detect it, then notice the lightning strike, count, and you can estimate. And that's because light travels at the speed of light, which is really, really fast. Sound travels much more slowly. Okay? So, the speed of light, let's review that one. What symbol do we use for speed of light? C is equal to 3.00 times 10 to the 8th meters per second, which is really fast. That would be going around the equator about 2.5 times in a second. I mean, that's fast. Okay. That's really fast. Okay. But compared to that, like we just said, the speed of sound, and what symbol do they use? They just use V for sound. I'm going to put it that way. In dry air, at 1 atmosphere pressure, 0 degrees Celsius, is 331 meters per second. That's a lot less, okay? That's 10 to the second. That's 10 to the 8th. So that's 6 orders of magnitude. Light travels 1,000,000 times faster than sound. Okay, a lot of difference there. The changes in humidity and temperature cause variations in the speed of sound, and the speed of sound increases with temperature at the rate of 0.61 meters per second per degree Celsius. So 0.61 meters per second per degree Celsius. So it's not a lot of difference, but a little bit. Okay? So the speed of sound in dry air at 1 atmosphere of pressure is then given by this. V is equal to 331 meters per second plus 0.61 meters per second per degree Celsius times your temperature in Celsius. Okay?
Why do we add that rate? I mean, why do we?
Because that's, I'll go put, I'm trying to get my pen to work. Okay. Because that's how much the speed of sound increases by, which is an addition. For every degree of Celsius, it goes up by 0.61. And remember, this was at 0 degrees Celsius. So for every degree Celsius, it goes up. Yeah. Okay.
I mean, typically there's never a constant like that.
What's that?
It's typically not going to be a constant.
Not, yeah, right, yeah. Because very seldom are we 0 degrees Celsius. Thank goodness. That's freezing point. Okay, I don't like freezing point. Okay, so yeah, but it's not a lot. So right now we're around 20 degrees Celsius. So 20 times 0.61 would be rather than 331, it would be 343 meters per second. So it's not a big difference. Okay? That's, my decimal is there. I don't know if you can see it. Okay. There is the decimal. Okay. 12.2. So about 343. Just add 12 meters per second. Not a lot of difference. Okay? So we do everything by rules of thumb. Now, if you wanted to do it in Fahrenheit, and this formula should dissuade you from so doing, you would need to be in feet per second, which would be 1,087 feet per second, because a foot is shorter than a meter, so you need more of them, plus 1.1 feet per second per degree Fahrenheit, but a degree Fahrenheit is smaller. But because you don't start degrees Fahrenheit at 0 degrees Fahrenheit, you start at 32, which is the freezing point of water, then your temperature in Fahrenheit, you'd have to subtract 32 from it. Okay? And who wants to go through all that? Okay? Let's stick with Celsius. It's so much, and metric, so much easier to deal with. Okay? But I bet you they're going to give you some of both, aren't they? Okay. So, let's look at example 1. Now, I'll probably need to erase these, so hopefully you got your formulas right. So let me erase these and do example 1 here. Find the speed of sound in dry air at 1 atmosphere of pressure if the temperature is 23 degrees Celsius. Which is probably not too far off from what it is outside right now. No, it's probably a little below that. Because when I drove in, it was right 73 degrees, and 20 degrees Celsius is 68. So we're not far from that right now, but it probably dropped a little bit. So your temperature here is 23 degrees Celsius. That's probably not far off from 75, something like that, Fahrenheit. Okay, we want to know velocity of sound in dry air at that temperature. Okay, so we use the formula we had. which was 331, right? Meters per second, plus 0.61, was it?
Right. 0.61.
Yeah, 0.61 meters per second per degree Celsius times 23 degrees Celsius. And see how friendly your units are to you? Degrees Celsius cancels out, and that gives you meters per second to meters per second. So someone with a calculator, 331 plus 0.61 times 23 equals. Now, I'm not about to do that one in my head. I would really get a headache. Say again?
345 meters.
That sounds reasonable. Did everybody get it? Because we just did it for 20 and we got 343. So yeah, that sounds about right. Everybody got it? Let's see what the book got. 345. Good for them. Okay. So just 14 degrees difference. 14 meters per second different. Not very much. Okay. Now, what is the time required for the sound from an explosion to reach an observer 1,900 miles away? So the distance is 1,900 miles. And even though they have 4 significant digits there, nothing we had before gave us 4 significant digits. And I'm really surprised they stuck with 3 significant digits in the earlier one, because the 0.61 is only to 2 significant digits, but we won't tell, okay? We'll let them get by with that, okay? And this will be meters, yeah, meters away. So that's 1.2 kilometers, 1.9 kilometers away. Almost 2 kilometers away, which is, let me see, 1.2 miles or something like that. So this is pretty far away. So what time will be required for the sound from an explosion to reach the observer for the conditions in example 1? So we have distance, we have velocity, that's this thing, okay? And we're looking for time. That's the unknown. What is the time required? So how do we relate distance, speed, and time? Anyone remember? Oh, no, that was several chapters away. We didn't need that now. We're just talking about sound. No, that's why we did the stuff several chapters away.
Did we do that chapter 4? Motion? I don't think we did it.
Well, let's see.
It said that it's from the formula in chapter 4.
Oh, really?
I don't think we do chapter 4.
No, we didn't do chapter 4, but we use that same. Okay, where did you see that?
It says on page 437.
Okay.
Use the basic equation, which says S equals VT.
Oh, from section 4.1. Okay. Okay. All right. Okay, we didn't do 4.1, but when we were doing let's see, where was it? When we were talking about forces, we had to start with distance, speed, velocity, acceleration. We went through all those. We used the stuff from there, but yeah. So I don't know if we we must have had the formulas. I don't have my notes here to go through them, but but y'all know this, by the way. Don't you? Okay, give me representative units of velocity, some speed you've gone in your life.
Miles per hour.
Miles per hour. What does miles measure? Distance. And hours measures? Time. So you just said velocity equal distance over time, didn't you? Miles per hour. right? There's your formula. Okay? Now we're looking for time, so what would we need to do? I don't know if you want to do it the Navy way or...
Distance divided by velocity.
Yes, you're absolutely right. Time is equal to distance divided by velocity. You got it. So that would be 1,900 meters divided by 345 meters per second. Huh? Okay, what in the world? Okay, there we go. I don't know what. I don't think I'm doing anything, but maybe I'm not doing anything. Okay. All right. Just winking in and out on us. Okay. Notice our units, your friends, our units. Meters cancel out, and you have 1 over 1 over second, which is seconds. So the time will be measured in seconds. It looks like it's going to be less than 6, doesn't it? Second? T is about what? 5.51, is that what you said? That sounds reasonable. Almost 6 seconds. Let's see. Oh, look at that. That's what they got in the book. Now, were you reading from the book? Or, no. Okay. No, you had done it. Okay. 5.51 seconds. Very good. Okay. Now, everybody got that? See how it happens? Even though we didn't do chapter 4, I think we still did those kind of measurements. Okay? Let me get out of this if everybody's got it, do they? Okay? We get out of here, throw it away, and go to the other. All right? And go from current slide. All right. Just under example 2 there that we just did on page 437, sound propagates faster in a dense medium, such as water, than it does in a less dense medium, such as air. Well, why is that? The pressure, the air molecules are further apart, so it takes more, they just don't move as fast as they do. Whereas water, the molecules are right next to each other, and I think you probably, if you've ever been swimming and been underwater, you notice the sound is sort of amplified, under there, Now, when you were children, you may not have watched the cowboy and Indian movies and shows and stuff. When either the bad guys or the Indians wanted to know if a train was coming down the track, what did they do? On the rail, and they could hear it way sooner and everything than if they listened in there, because that metal is much denser than air. So it's the sound will travel much faster and more without as much loss. Okay, so here are a few of our media. Aluminum. Boy, look at that, 6,420 meters per second, as opposed to 331 in air. Brass, not quite as dense as aluminum, so 4,700. Steel, those rails on the railroad track, almost 6,000. Granite, whoa, that's rock, 6,000. Alcohol, denser than air, but not nearly as dense as any of those others, is about 1,200. Water, about 1,500. Air, of course, 331. Now this is at 0 degrees. And a vacuum, that means no molecules there to bounce off of, won't travel at all. Nothing to compress and rarefact. So it won't travel through a vacuum. Okay? So, and in feet per second, they just do that conversion there. And you recognize that 1090, they rounded to 3 digits where they had 1087 in the green box on the previous page. Okay. All sounds have, oh yeah, and by the way, if y'all are doing sonography, you're going through all sorts of different media, mostly fluids, because if it's for a fetus in utero, then you'll be the embryonic fluid, it's pretty much water, so you'll be, the speed will be more like water than it will be air. All sounds have characteristics we associate only with that sound, blah, blah, blah. So here's a few of these. I guess I'll go back to the other page. And well, let's just see what's next here. Wow. Don't need this again really soon. Let me just write them on the edges if I can. One of these is intensity. Whoa, let me get my pen set up. Okay. Intensity is how much energy that sound wave has. So how powerful it is. That relates to loudness, by the way, but we'll see. The intensity is basically the energy transmitted by sound per unit time through a unit area. Thus, it's power divided by area. Okay? Loudness refers to the strength of the sensation of sound heard by an observer. Okay? Describes how strong or faint the sensation of sound seems. So it would sort of be related to the intensity. No. Now, the ear does not respond equally to all frequencies, especially if you have hearing loss. And all of us have some hearing loss. Some of you may be young whippersnappers, but once you get a few years, the frequencies you receive go down. And actually, this happened, I believe, in London when cell phones first came out, and they had the different dial tones. What did they call those? But you could have a different ringtones. Yeah, that's what they were, ringtones, for different people calling. And students in an English school found out that all their teachers, old people that they were, couldn't hear the high frequency ringtones, so they all set theirs for pretty high frequency, and they could call each other in class, and the teacher would never hear them. Until they had a young teacher who had excellent hearing, and she found out what they were doing, because she could hear their ringtones, maybe not as well as they could, but could hear them, so the phones got confiscated. Okay, they lost them. But it's pretty amazing what we have. All right, now, levels of intensity are also measured on a logarithmic scale, because if you remember, our range is just amazing. Thousands-fold differences, okay? And the levels of intensity are measured in bells, B-E-L. Now, you might think that's the ringing of a bell. No, that's not where it came from. It came from Alexander Graham Bell, exactly, who came out with the telephone, the phonograph, and many other things like this. This shows how weird physicists think. I don't know if anyone ever thought, they must have, but a former pastor at our church who lived to be close to 100 just recently died, and his last name was Alexander. So after he died, they wanted to name the bell tower after him. So they named it the Alexander Bell Tower. So I think of it as the Alexander Graham Bell Tower. Of course, that's not what it, never mind. Okay. So, weird. Okay. And with that in mind, here are some of those, and we measure these in bells, but a bell is a bit of a large number, so they take 1/10 of a bell, which is a decibel, and that's where we get the decibel range, okay? And that's why the B is capitalized, because it was named after Alexander Graham Bell. So dB, that's decibel, okay? You probably have heard of decibel. Now, the threshold of hearing would be 0 decibels. Now, that would be for someone with very good ears, too. I would not hear a 0 decibel, okay? Say again?
Would that be like a little ringing noise in the TV and makes me
Possibly, yeah. That might bug my wife when I say, what are you talking about? So, possibly, okay? Minimal sounds that most people might be able to hear would be around 10 decibels. The ticking of a watch, you mean watches tick anymore? Okay. Some do, but I don't hear them. 20 decibels. Whisper would be about 30 decibels. I don't usually hear those either. Leaves rustling or refrigerator noise, around 40 decibels. Okay. Now notice how these are related with intensity, which is watts per square meter. Every time you go up a power of 10, you go up 10 decibels. So the power of 10 is related to 10 decibels. And that's why it's decibels, because it's 10 of them, okay? So the sound at the threshold is scarcely audible. A whisper is very faint. I probably wouldn't hear that one. Average home and neighborhood street, about 50 decibels. That's moderate. I'll hear most of those, okay? I don't hear it when the dog scratches in her kennel downstairs. My wife hears every bit of it, but I don't. Normal conversation or a microwave. I didn't know microwaves were that loud. That's about 60 decibels. Car alarm, city traffic, around 70. That's getting in the loud range. Your garbage disposal, vacuum cleaner, outboard motor. I think vacuum cleaners vary a lot. Noisy restaurant, that's around 80 decibels. That's very loud. Factory, electric shaver, screaming child, around 85 decibels. Lawnmower, passing motorcycle, depends on whether they got a muffler or not. Convertible ride on the freeway, around 90 decibels. Okay. Hair dryer, diesel trucks, chainsaws especially bad. Helicopter, subway train, around 100 decibels. A car horn, I thought they mentioned that, but no, a car or alarm clock. I'm sorry, I read that as a car alarm. Okay, car horn or snowblower, around 110 decibels. That can be deafening if you hear it too much without protection. Actually, I think chainsaws hurt your ears too, so I would almost put them up. Rock concerts, prop planes, around 120 decibels, painful. If it's not painful, that means you've already lost your hearing, okay? 100 feet from a jet engine, air raid, siren, that kind of stuff, 130 decibels. Shotgun blasts, fairly close to you, 140 decibels. You can do some damage with those without the sound suppressors. Please use sound suppressors, okay? This is from the Better Hearing Institute, Self-Help for Hard of Hearing People. Who would that be? Okay. All right. Those are just some of the ranges there. Now, let me throw out a few other terms. Pitch. You probably heard of this. I even probably mentioned it a little earlier when I talked about someone who sang well, had perfect pitch, they would say, or very near perfect. The pitch of a sound is the effect of the frequency of the sound waves on the ear. The higher pitched sounds have higher frequencies than lower pitched ones. So basically, you're talking frequency there when you're talking pitch. Okay? They may measure them slightly differently, but that would be pitch. And then they get to the figure of the human ear. Amazing thing that this is. What is this outer part? They call it the auricle. Does it have a purpose rather than being this weird-looking thing on your body? Have you? Yeah.
It takes the sound in.
Yes. picks it. You remember the old people who were deaf many years ago had this big old horn that they would have hold up to their ear, sort of like a horn of penny. It captured more waves and sent them in. That's exactly the purpose of the auricle. I'm surprised mine hasn't grown to try to compensate for my lack of hearing. And then the external auditory canal, I know mine is big, and it probably was big from birth because I probably wasn't able to hear, because I never could used to, when they had one-size-fits-all earplugs, they always fell out because my ear canal was bigger than most. Okay? Now, they don't say much about it, but these are bones, porous bones around your ear. And the reason I mention that, have you ever heard yourself on tape? Did it sound like you? You didn't think so. Everybody else says it sounds just like you. The reason is what we hear is mostly sound that's transmitted through the bone, whereas everybody else is sound that comes in this way. Okay? And we had some good friends of our family that one Christmas, the guy brought a tape recorder. That's when tape recorders were just becoming to be fairly affordable and, you know, usable and stuff like this. And he brought it and sort of just for fun, turned it on without telling anyone, set it under the kitchen table, and everybody was sitting around talking. And then later he played it back. And my mother said, "Who is that that's talking all the time? Making all," you know, of course, the only voice she didn't recognize was hers. My father liked to die, you know, with laughter. And Andy got so embarrassed because Mom was not too pleased with that. Turn that thing off. Okay, I remember that. So the sound waves, those pressure waves, go into the canal, and here they hit the tympanic membrane, which also has another name. Tympanic? Eardrum, exactly. Exactly, that's your eardrum. Okay? Now, then this is called basically the outer ear, I think. Yeah, external ear. And the eardrum, or the tympanic membrane, is that divider, and or right at that's the entrance to it. Then you get to the middle ear, and basically, I think this is called the hammer and the something else. They used to have hammer and anvil. That's it, hammer and anvil. Just little bitty vibrations here get amplified here, in a sense, and that's the mallet, hammer, mallet, you know, incus. I guess it looks like an anvil there, and what in the world does that say? Stapes or, look in the book. Yeah, stapes in the oval window. I don't know what that means, okay? But anyway, that's what that is. And that then bangs on something here. And there's all sorts of fluids and things in here. And you don't need to know all this, but then the inner ear, that's where really everything happens. I mean, it all depends on what's going on out there. Now, what is this? Eustachian tube. What in the world is that? Does anyone know? All right. Have you ever flown before? Okay. Have you ever noticed what happens to your ears? They pop. Okay. And why? And also, if you've ever gone up steep mountains or come back down or whatever, you'll feel popping then too.
They pop when you go below sea level too.
Yes, and when you go underwater, you'll feel the popping. Have you done some diving and stuff?
No, I just been more.
Yeah. Right, okay. Now, what happens, you're changing the external pressure, which is here, while your internal pressure doesn't change. You can do some pretty serious damage to your eardrum, the tympanic membrane, because it could get pushed out if that pressure decreases, like going up in a plane or driving up a mountain or something. So what this is connected to the back of your throat, and it allows the pressure release. Now, they don't want a lot of stuff going from there, so it's a pretty thin thing here. And young kids, if they get, say, an infection or something, and their eustachian tubes are pretty small, and something swells up there, and they don't get, you take them in airplanes, and you can sometimes have screaming kids, you know. You may have been in one. And, of course, the screaming helps open that a little bit. And what they say to do is, you know, this kind of stuff to force pressure in to equalize pressure or whatever. So that's connected to the back of the mouth to keep the pressure off. But then here is in the inner ear, this is where the real activity goes on. And the cochlea, and that's just like a cochlea, and is that how you say it? People with hard of hearing will sometimes have cochlear implants, and they put something that will do the same job, but it's man-made in there. My wife works with, I don't know if any of you ever heard of CMV, cytomegalovirus. It's a herpes virus, and it typically, I mean, you or I could catch it if you have already been exposed to it. My age, I'm certainly must have been exposed to it. But if a woman who's pregnant gets exposed to it and she transmits it to the child in utero, then that can cause all sorts of things. If you and I caught it now, it'd be a mild case of flu or less, you know, and no sequelae, no after effects or anything, unless you have a really, really bad immune system. For instance, people with advanced stages of HIV or AIDS, you know, when their immune system is basically shot, CMV can do a lot of damage to them too, and typically can and does. But for young kids in utero, they could have problems, and then when they are born, they can have all sorts of hearing problems and other problems too, but hearing is the most common. So a lot of the kids that she has studied and stuff, some of them will have cochlear implants and stuff. And you have all these other things. But this is where the nerves connect, and the nerves pick up these signals that have been amplified and purified or whateverified and stuff, and then send those to the brain, and the brain sorts them out, and you hear. It's really an amazing system. Now, you don't need to know any of that, but that's still pretty interesting.
And it also really affects your balance, right? Like
Yeah.
If you have vestibular issues, your balance.
Yeah.
That mean you're
Yeah, and that's all inner ear type stuff. And, you know, when kids have tubes put in, that's usually what the tube is for, is to balance some of that pressure and stuff like that. All right, that was probably more than we needed to do on that. Okay. The next issue here, and I think, how are we doing on time? Oh, yeah, we got time. So let's go back to the other. And go from current slide. And let's talk about the Doppler effect. Have y'all heard of this? What have you heard? What? Ooh, I have to change my pen again.
About a submarine.
A what?
A submarine.
Okay.
I don't know why.
Okay, say again. Weather. Okay, Doppler radar. Okay, is all that is good. Now, the Doppler effect on the submarine is very interesting. You bring that up. I didn't know anyone but sonarmen knew about that. But, you know, a trained sonar technician listening to that can actually tell how many blades are on the propeller of a given ship, how many propellers. If one of them has a nick in it, that's going to make, so, and then whether it's approaching you or going away because of the shift in frequency, the Doppler effect. So that's amazing that you could pick up on submarine like that. See, submarines can detect ships way before a ship will ever detect a submarine, okay? Because ships make a lot of noise. Submarines are usually running fairly quietly. So that's why they're pretty formidable weapons, okay? So the Doppler effect refers to the variation in frequency heard when the source of the sound and the receiver of the sound, your ear, or whoever's ear, are moving relative to each other. Now, you could be moving toward the source or the source moving toward you. Most of the time, it's the source moving toward you if you're fairly stationary. And you'll notice this a lot with, say, a siren coming. And certainly it'll get louder as it gets nearer, but also you'll notice the pitch goes up, where if it's going away from you, the pitch will go down, meaning frequency, but also the loudness goes down. So you'll get those confused. They are doing sort of the same thing, but the effect of this is that change of pitch or frequency. As an automobile or a train passes by at high speed, sounding a horn or a whistle, the frequency or the pitch of the sound drops noticeably once it passes and starts going away. It doesn't change on the device. It sounds like they change it when they pass you, but they don't. That's actually the Doppler effect. By the way, that's named after variation in pitch. It's called the Doppler effect after Christian Johann Doppler. I think he was probably, Austrian. I was going to say German, but Austrian. Okay. There was actually, any of you watch The Big Bang Theory? Okay. Many years ago, there was one. I don't see it often, but I remember seeing this one when, what's his name?
Sheldon.
Second?
Sheldon.
Sheldon. All I could think of was Sherman. I knew that was it. Sheldon was invited to some sort of costume party.
Oh, you're talking about he dressed up as the Doppler.
As the Doppler effect, and it had a wave, close frequency on this side, far apart on the other side, and they just thought he wore a weird T-shirt. He said, no, this is a Doppler effect. So you remember that one.
Yeah.
I thought that was, it's so amazing. That show has a lot of science in it. It has a lot of silliness, in it too, but it does have an amazing amount of science in it. So let's see. I guess we'll go straight to the formula. And here's what it is. F prime, that's a frequency, and this is the Doppler shifted frequency. It's not the one emitted by the source, but it's the one heard by the receiver. That's equal to F, that is the actual frequency. So the source frequency. Okay, the one actually done. The frequency of the horn, the siren, the whatever is blaring, that's the actual frequency. This is the one you hear. Okay? That will be multiplied by the speed, and that's the speed of sound. Okay, which is usually fixed by the temperature and other conditions, divided by V plus or minus Vs. And this is we're assuming now you're stationary and the source is the thing moving, which most of the time that's the case. The police car, the siren, the fire truck, the train, whatever, that's the thing moving, you're fixed, and that's the speed of the source. Okay, so both of these are speeds of the sound, and this is the speed of the source. I can't spell. Okay. Now, we have a plus or minus there. Now, here's what you have to think of. All right. when you increase the denominator, you decrease the other side. That's an inverse proportionality, right? So if you make the denominator a bigger number, that makes this a smaller frequency. So when you have the plus here, that's when the object's moving away from it. Okay? That's when the source is moving away. When you have the minus here, that makes because nothing travels at the speed of sound, okay? Except jet aircraft, okay? And you're not going to be listening to many of those, I hope. Okay? So when you subtract this from that, that makes your denominator smaller. That makes this frequency higher, and it goes up. So that's the Doppler effect. Okay? So like they say here, the plus in the denominator is used when source is moving away. From the receiver. Minus is when the source is moving toward. Make sense? Okay? So the frequency is going up when it's moving toward you, going down when it's moving away. And remember, the denominator is inversely related to the numerator. Okay? What's on the other side. And think of this. Which is bigger, 1/2 or 1/3? 1/2, but the 2 is smaller than 3, right? So when the number goes up in the denominator, that means the other side is going down. All right. I think that leads to the next figure. So let's go out of this and go back to this. Sorry about all this changing around. We almost have to do it. Okay. From current slide. Okay. So, let's say this car is moving, and it's not going to hit either one of these people, but they're standing off and it's moving. So let's say the car is moving away from the gal there and toward the guy here, toward A and away from B. Okay? Now let's just say this car has a terrible muffler, okay? And it's making lots of noise, okay? So as it comes closer to the guy, it's going up in frequency, but going away from the gal here, the frequency is decreasing. And why is that? Well, remember, sound waves are pressure waves. So the sound waves coming off of the car are pressure waves. But when the car is moving toward them, it makes those waves closer together. Moving away from the woman, it's moving them further apart. So therefore, the frequency is greater for him, less for her. Now, yeah.
Is that directly proportional to loudness, or is that
Okay, the loudness is also there, but that's not. This is frequency, the wave spacing. That's cycles per second, pulses per second. These are coming to them at a higher frequency than those going to her. The loudness is just because it's getting closer. Okay, so you have two things going on, and they sort of. You'll notice both of them, but the frequency is the pitch. You'll notice it's going up, as you come closer, and then goes down, and it's going further away. Loudness is also there, but it's the frequency that is the Doppler effect. That's the pitch. Okay? Now, I think we're ready for example 1. Okay? So I think, let's just make sure. Yeah. Let's go back to, sorry about this. The other, current slide, and I better change my pen. I don't know why it goes to red. You think it would default to black, but it doesn't. Never has, and I guess never will. Okay. An automobile sounds its horn while passing an observer at 25 meters per second. So what would that be in our formula we just had? Remind me of that formula. That was F prime is equal to F times V over V plus or minus Vs. Okay? So what would this 25 meters per second what one of those symbols would that represent? The car is passing the observer at 25 meters per second. The car is the thing sounding its horn. So which of those symbols represents the 25 meters per second? Anyone make a guess? You have 1, 2, 3, 4 symbols up there. You have a 1 in 4 chance of getting it right. V sub s, absolutely. So the V sub s is equal to 25 meters per second. I was just going to say, the units will tell you it's got to be one of the two velocities, so it's down to 1 out of 2. So it's V sub s. The actual horn frequency is 400 hertz. So which one of those symbols represents the 400 hertz? The actual horn frequency. That is your F. Okay. Assume that the speed of sound is 345 meters per second. What would that be? That's your V there, the speed of sound. So that means we're above freezing, okay? We're not down there at 331, we're at 345, which is about 20-some degrees Celsius, so that's pretty reasonable temperature. So reasonable speed, okay? Now, that's what they've given us. Assume the speed of sound is that. What is the frequency heard by the observer when the car is approaching? So what would that be? Only symbol left. F prime is what we're looking for, okay? The Doppler shifted sound. And what would that be? Yeah, 400 hertz. 345 meters per second divided by 345 meters per second. Now the big question. Which symbol do we use? Which operation do we use?
It's decreasing, minus.
So we use the minus, what? 25 meters per second. Notice your units are your friends there. Everything's balancing out. They're going to cancel out, so you're going to have frequency on the other side. Yes, I love it, don't you? Okay. Of course you do. 400 hertz times 345 meters per second divided by, I can do that subtraction, 320, right? If the numbers would stay up there, meters per second. Notice the meters per second cancel out, okay?
1.08.
What's that?
1.08.
Is that thing in there? Multiply that by 400. 439? 31 hertz. Okay. Let's see how the book did. Oh, look at that. They did it right. Good for them. Okay. Now, what is the frequency heard when the car is leaving? What would be the difference here? Yes, you add in the denominator. The 400 hertz stays the same. The 345 meters, I can't write. I say 345 and I write 354, okay? Something's wrong with my brain, okay? Well, we won't get into how that much, okay? 345 meters per second. Whoa, okay. Over 345 meters per second. Plus, this time, as you said, 25 meters per second. So that will be 400 hertz times 345 meters per second divided by, this time that's 370, isn't it? Meters per second. I'm adding in my head, so I hope I did it right. And what do you get the going away frequency to be? Very good, 373 hertz. Does everybody see that, understand? Does it make sense? So the frequency is going down when the person so that you'll notice it most. You'll notice some as it's approaching. Mostly that'll be loudness, but you'll notice a change when it passes. You know, from a high frequency to a lower frequency, and quite often, especially the larger speed it's going, that'll be significant change of pitch. And they're both close, so the loudness won't be changing that much then. That'll be mostly the pitch. Okay? Now, there is a example there on ultrasound under physics connections. That could be you one of these days, right? And pretty incredible what computer can interpret that to be. Ultrasound is used to examine tissue and liquid-based internal organs and systems without subjecting the patient to invasive procedures. Now, I actually had one when I had this young doctor, and he seemed like he was nervous about everything. And he said I had some microuria or something like that, meaning microscopic amount of blood in my urine. Didn't see anything, but he said, oh no, it's really small. I think we need to do an ultrasound. Okay. No, wait. Was that something? I think he was going to do something. He was going to do an invasive thing, and what do you call it? And they run something up and, you know, start checking out the bladder. Well, my wife said, no, way too invasive. So we left him and went to UAB, talked with a much more reasonable urologist. Well, number one, he was just an internal medicine guy. She said, if there is something, let's go to a urologist. Our friends knew him fairly well. We went there, and he had him do an ultrasound. They said, don't drink anything, because what the guy was suspecting was wondering about bladder cancer. And so rather than going up, sending a scope up, looking around, said, let's do an ultrasound. Far less invasive. So they said, don't drink anything. Drink plenty, but, well, let's see. There was certain conditions, but don't urinate for so many times before your appointment, because they wanted the bladder full, so it was fully pumped out, you know. And then they gave me something to drink when I went in there that would make good contrast. And then they started looking around my bladder. She said, wow, you've got a full bladder. I said, yeah, I know. But they said to, yeah. And then she looked around. Bladder looked good, but she started looking elsewhere. She noticed a little shadow near a kidney, and had bringing in other people. Of course, she hasn't told me what the deal was yet, so I thought they had found something in my bladder. But no, I think she had said the bladder looked good, but she kept looking around, yeah, and brought in somebody else, and and brought in somebody, yeah. So everybody was in there looking at this. What's going on here? Well, there's a little shadow there near a kidney, but we can't tell. And she said, it could be gas or it could be something else, so we'll need to do some further testing. But your bladder's fine. It's perfectly clear. Please go use the bathroom. You look like you're about to explain. So anyway, it turned out that when they did another more sophisticated test, it wasn't ultrasound anymore, but they found that I had angiomyolipoma. Angio means blood, myo means muscle, and lipoma is lymph system. Okay, lymphoma. And these little, they're sort of like a hard knot, a growth, you know, it's just fatty tissue, but I had a whole bunch of them near my right kidney. And one of them was pretty large, like 4 centimeters. No, yeah, I think so. That was pretty large. And they said, that could rupture, given a certain, and you'd bleed to death before we ever could get you and find out what was going on. And so they decided to take it out. So that little panicky doctor who was worried about and I asked the urologist later, I said, well, how about this microarteria? He said, oh, yeah, you have a little bit. Who pays any attention to that? Most people have that. Yeah. New doctor, he was sort of concerned. So anyway, so that's when I had my ultrasound. I wasn't pregnant either, so it was. But they use ultrasound for all sorts of diagnostic tools. Okay, problem set 16.4. There are, 19 problems there. The odds are in the back, so I would definitely give a look to those. Okay? And if I were you, I'd read up on that ultrasound, because that may be what you're doing one of these days. Hopefully you will be.
On number 19, we have to use the conversion.
Say this again.
Look at number 19.
Oh, 19. Okay. A construction worker 30 meters above the ground drops his hammer. Shame. How long does his shouted warning take to reach the ground if the speed of sound under these conditions is 345 meters per second? No conversions there, because it's meters and meters per second. You'll find. Yeah. Your answer will be in seconds. Okay. And the how long there means time-wise, not how long a distance, how long time. Okay. All right, good deal. Thank you. More things to grade. All right. Well, I don't think we have time to get started in resonance. Okay, so we'll pick up there next time. All right. I thought I had gotten a pencil out, but I don't know. There it is. Okay. Oh, good. Something else to grade. Thank you. Did you get the lesson?
Chapter 12.
Yeah, chapter 12. Okay. All right. Yes. Oh, you got one too? Okay, super. Okay. It took me a while to find it before. Hopefully I'll get it sooner this time. A4 solve. That's it. Okay, now. One to watch, two, it's one question, but 2 places. They put the weirdest number there, 50,00. What does that mean? They left off a 0. It's 50,000 pounds. I had to work it out to see whether they meant 5,000 pounds or 50,000 pounds. It's 50,000. And then this part, that's 60,000. So I tried to correct it there, but that's the only different thing there. Okay? All right, glad to. All right. Yes.
Does this class meet the Wednesday?
Say again?
Does this class meet the Wednesday before Thanksgiving? I looked on the calendar.
No. There's no classes on that whole week. Okay. We have professional meetings Monday, Tuesday, and Wednesday, and then Thursday, Friday's a holiday. So, yeah, no classes the whole week of Thanksgiving. Now, the Wednesday before that, yeah, but the week of Thanksgiving, yeah. Uh-huh. And by the way, good news, bad news situation. Bad news is Columbus Day is coming up, and that's the state holiday. But the good news is it's a Monday, not a Wednesday, so we won't miss class. All right. I knew that would throw you no end. Okay. All right. Veterans Day. I said Columbus Day, didn't I? Veterans